Grounding for safety is extremely important when dealing with a 480-volt three-phase ungrounded delta system. To start addressing the source side of the transformer, install a ground rod at the power source. Connect a grounding conductor using 8 American wire gauge copper or equivalent from the ground rod to a grounded conductor, effectively creating a neutral point for the three-phase delta system. Subsequently, connect a grounding lug to the frame of the machine and run a grounding conductor, this time using 12 American wire gauge copper or equivalent from the lug to the neutral point created by the ground rod connection. Now, regarding the motor itself, the motor frame must be grounded to prevent electric shock. Install a grounding lug on the motor frame and connect it to the grounding conductor originating from the transformer. Moving on to the 120-volt side of the transformer, there are two options. Option 1, which is recommended, involves isolating the 120-volt circuit using an isolation transformer. This approach creates a dedicated ground reference and eliminates the need for a separate grounding conductor. Option 2 involves installing a grounding lug on the 120-volt side of the transformer and connecting it to the grounding conductor from the transformer. Ground one leg of the 120-volt circuit, typically the white wire, to the frame of the machine. This establishes a common ground reference for the 120-volt circuit. In addition to these grounding measures, implement these additional safety considerations. Firstly, install overcurrent protection devices, such as circuit breakers or fuses, on all 480-volt and 120-volt circuits. Secondly, use double insulation on all 120-volt components to prevent electrical leaks. Thirdly, provide emergency stop buttons and interlocks to prevent accidental operation. Fourthly, ensure that all metal enclosures are properly bonded to the grounding system. After the grounding is complete, it is essential to perform several tests to verify its effectiveness. Firstly, conduct a continuity test between the motor frame and the grounding lug on the transformer. Secondly, perform a continuity test between the grounding lug on the 120-volt side of the transformer and the frame of the machine. Thirdly, conduct an insulation resistance test between the 480-volt and 120-volt circuits. By following these guidelines, you can ensure the safety of the scissor lift truck when operated on a 480-volt three-phase ungrounded delta power source. To elaborate on grounding, it's crucial to understand its fundamental role in electrical safety. Grounding, in essence, provides a low-impedance path for fault current to return to the source, thereby facilitating the rapid operation of overcurrent protective devices like circuit breakers or fuses. This rapid response minimizes the duration of fault currents, reducing the risk of electrical shock and equipment damage. In the context of the 480-volt three-phase ungrounded delta system, the absence of a direct connection to ground presents unique challenges. An ungrounded delta system can continue to operate even with a single ground fault, as the fault current has no immediate return path. However, this situation is hazardous because the voltage to ground in the remaining two phases increases, potentially stressing insulation and increasing the risk of a second fault. A second ground fault on a different phase would create a phase-to-phase fault, resulting in a high current flow and potentially severe damage. The recommended practice of installing a ground rod and connecting it to a derived neutral point of the delta system effectively transforms it into a corner-grounded delta system. This approach provides a defined ground reference, allowing fault currents to flow and protective devices to operate. The size of the grounding conductors specified as 8 American wire gauge for the connection to the ground rod and 12 American wire gauge for the connection to the machine frame is determined by the anticipated fault current and the requirements of the National Electrical Code, or NEC. The NEC provides tables and guidelines for selecting appropriate conductor sizes based on the size of the overcurrent protection devices. When grounding the motor frame, it is imperative to use a dedicated grounding conductor and not rely on the metal conduit or other structural components as the primary grounding path. The grounding conductor should be securely connected to the motor frame using a grounding lug and should be routed back to the main grounding point in a manner that minimizes impedance. The two options presented for grounding the 120-volt circuit derived from the transformer offer different levels of safety and performance. The recommended option of using an isolation transformer provides the highest degree of isolation between the 480 volt and 120 volt circuits. An isolation transformer has separate primary and secondary windings with no direct electrical connection between them. This eliminates the possibility of a ground fault on the 480 volt side propagating to the 120 volt side. The second option of grounding one leg of the 120 volt circuit is a more conventional approach, but it does not provide the same level of isolation as an isolation transformer. In this configuration, a ground fault in the 480 volt side could potentially transfer to the 120 volt side, although the grounding conductor should limit the voltage rise and facilitate the operation of overcurrent protective devices. The additional safety considerations, such as the use of overcurrent protection devices, double insulation, emergency stop buttons, and bonding of metal enclosures, are all essential for ensuring the overall safety of the scissor lift truck. Overcurrent protection devices, such as circuit breakers or fuses, are designed to interrupt the flow of current in the event of an overload or short circuit. These devices should be properly sized to protect the conductors and equipment in the 480 volt and 120 volt circuits. Double insulation provides an extra layer of protection against electric shock by ensuring that all exposed metal parts are insulated from live electrical components. Emergency stop buttons provide a means to quickly de-energize the equipment in the event of an emergency. These buttons should be readily accessible and clearly labeled. Bonding of metal enclosures ensures that all metal parts are electrically connected to the grounding system, minimizing the risk of voltage differences and electric shock. The verification tests, including continuity tests and insulation resistance tests, are critical for confirming the effectiveness of the grounding system. Continuity tests verify that there is a low impedance path between the various grounding points, while insulation resistance tests verify that there is adequate insulation between the energized conductors and ground. These tests should be performed after the grounding system is installed and periodically thereafter to ensure that it remains effective. In summary, grounding a 480 volt 3-phase ungrounded delta system requires careful attention to detail and adherence to established safety practices. By implementing the recommended grounding measures and safety precautions, you can significantly reduce the risk of electrical shock and equipment damage. It's also important to consult with a qualified electrician or engineer to ensure that the grounding system meets all applicable codes and standards. When dealing with electrical systems, safety should always be the top priority. It is vital to ensure all work is performed by qualified personnel who understand the hazards involved and follow proper safety procedures. The grounding conductor size is critical to ensuring a safe and effective ground fault current path. The 8 American wire gauge and 12 American wire gauge sizes mentioned are minimums and may need to be larger depending on the specific installation and the size of the overcurrent protection. Refer to NEC Table 250.122 for proper sizing of equipment grounding conductors. This table bases the grounding conductor size and the rating of the overcurrent protective device in the circuit. The ground rod itself should be at least 8 feet long and made of copper or copper-clad steel. It should be driven into the ground so that at least 8 feet is in contact with the soil. In areas with poor soil conductivity, it may be necessary to install multiple ground rods connected in parallel to achieve a low enough ground resistance. The connection between the grounding conductors and the ground rod should be made with a listed connector suitable for direct burial. These connectors are designed to withstand the corrosive effects of the soil and maintain a reliable electrical connection. It is important to note that the ground rod provides a path for fault current to return to the source, but it does not eliminate the need for other safety measures such as overcurrent protection and insulation. The ground rod is just one component of a comprehensive grounding system. When installing an isolation transformer, it is important to choose a transformer that is specifically designed for isolation purposes. These transformers have a high degree of electrical isolation between the primary and secondary windings and are often tested to higher voltage levels than standard transformers. The isolation transformer should be installed in a location that is easily accessible for maintenance and inspection. It should also be protected from physical damage and environmental conditions such as moisture and dust. The overcurrent protection devices used in the 480 volt and 120 volt circuits should be selected based on the ampacity of the conductors and the rating of the equipment being protected. Circuit breakers are generally preferred over fuses because they can be reset after fault, while fuses must be replaced. However, fuses may be more suitable for certain applications where a very fast response time is required. The double insulation used on the 120 volt component should be rated for the voltage and temperature conditions in the application. It is important to use components that are specifically designed for double insulation to ensure that they provide adequate protection against electric shock. The emergency stop buttons should be located in readily accessible locations and should be clearly labeled. They should be designed to be easily activated in an emergency even by someone who is not familiar with the equipment. The emergency stop buttons should interrupt all power to the equipment, including the 480 volt and 120 volt circuits. The bonding of metal enclosures is essential for minimizing the risk of electric shock. All metal enclosures should be bonded either using a grounding conductor that is sized according to NEC Table 250.122. The bonding conductor should be connected to the metal enclosures using listed connectors that are suitable for the application. The verification tests, including continuity tests and insulation resistance tests, should be performed after all grounding and bonding work is complete. These tests should be performed using calibrated test equipment and should be documented for future reference. The continuity test should verify that there is a low impedance path between all grounding points. The insulation resistance test should verify that there is adequate insulation between all energized conductors and ground. If any problems are found during the verification tests, they should be corrected before the equipment is put into service. It is also important to periodically inspect and test the grounding system to ensure that it remains effective. The frequency of inspections and tests will depend on the environment and the type of equipment being protected. In addition to the specific grounding recommendations provided, it is important to follow all applicable codes and standards, such as the NEC and local electrical codes. These codes provide detailed requirements for grounding and bonding electrical systems and equipment. It is also important to consult with a qualified electrician or engineer to ensure that the grounding system is properly designed and installed. Grounding is a critical aspect of electrical safety, and it is important to take it seriously. By following the recommendations provided and consulting with qualified professionals, you can help to ensure the safety of your equipment and personnel. Keep in mind, the specifics of the installation environment and the equipment being used will dictate the exact grounding requirements. Always refer to the NEC and consult with a qualified electrical engineer for any electrical work.